Well, good evening, everyone, and welcome to this Balticon presentation. I'm going to try to put up my slides. I believe that we're ready to go. So let me try to put them up on the screen and ask everyone if they can be seen. Now, the problem I'm having. I'm sorry about this.
You see your share screen?
Yes, I do, but I cannot. When I go to share screen, I don't see my desktop, the slides.
Reduce. If you have a full screen client, that will hide your desktop. You need to make your client be in a window so that you can see the rest of your desktop.
I'm sorry, could you say that again, please?
Go out of full screen mode into windowed mode so you can see your desktop, and then try share screen again.
Okay. Okay. Well, perhaps it might be easier. I sent my presentation file to Balticon Tech. Do you happen to have access to that?
I certainly can get it. I'll work on that while you see if you can make any progress. I'll
I
be
do
right back.
apologize. Yeah, I do apologize for the
I
delay.
apologize. We had a late shift in hosts. I didn't know I was hosting this until about 15 minutes.
Okay.
But it's
Thank you.
it's yeah.
So I hope our audience will be patient with us.
Yes, I hope so. Thank you very much for coming to this session. We
Um,
appreciate
I'm
everybody
delighted.
being here. We
Delighted.
appreciate you, and we appreciate the audience. Give us a moment here.
Okay. Thank you. Beautiful. Can you hear me now? Okay, wonderful. So then perhaps we can begin. And let me at the outset express my gratitude to all of you who are waiting so patiently, and like to express my thanks to those who are in tech support. Well, let me begin by introducing myself. My name is Gary Eden. I'm a professor of electrical and computer engineering at the University of Illinois in Urbana-Champaign. And the title of my presentation, as you can see, is What's New in Optical Physics and Engineering. And this evening, I'd like to focus on several recent topics, including water optics, literally optics that are made from water, imaging with lasers in both microscopy and at a distance, and something that you might find very fascinating, and it's called Nano Art. So I'd like to give credit to my colleagues at the University of Illinois, Andrei Baranov and Austin Steinforth, both of whom are amazing people and with whom I'm privileged to work. Well, the central feature of optical physics is the laser and optical sources. So if we could go to the next slide. Here we go. And hopefully there is some video. Is this the PowerPoint presentation, or the, I sent a PowerPoint presentation and it has several videos.
This is the PDF.
I see. Are you able to do the?
If I can find it, yes, I will.
Okay, thank you.
Sorry, this is what we found in the presentations. Let me go look again.
Well, thank you. Sorry for the difficulties. I sent both a PowerPoint presentation
and
a PDF.
I am seeing Dr. Eden PDF, and
Yeah, there's the
that's all
PDF.
I'm seeing.
Okay.
Oh, and I have a Balticon 2021.pdf, and I have a Dr. Eden.pdf, but they're both PDFs.
Oh, then somebody changed it to a PDF. Okay.
That's not good.
Yeah, if I can figure out how to share my, I have it on my desktop in PowerPoint, but trying to get it up onto the screen has proved fruitless thus far. Well, I mean, we can do it with the PDF. We just won't be able to see the videos. And perhaps afterwards I could resend the PowerPoint to you folks, and they could be put up on your website for others to see if you wish.
We have sessions to, we have places to put them, yes.
Okay. Well, let's just go back to the PDF, and I'll apologize to our audience for not being able to show the videos.
I'll see in the meantime if we have it hidden somewhere. I put a query out to see if we have it hidden somewhere else.
Okay. Thank you. They were sent in the same email.
I have a feeling somebody put two PDFs and no PPTX. Sorry.
That's okay. That's life.
Yeah. Again, my apologies.
No apologies needed, my friend. Thank you for doing what you're doing.
Okay, apparently, let me look.
There it is.
I see. We have it was unlabeled.
Ah, it was unlabeled. Okay.
It's labeled as Balticon 2021. It was not labeled with you. Our problem.
Oh, I see. I should have put my name on the label.
Yeah, okay. Let's open Google Slides here. I'm still sharing screen. Wonderful. Just a second, I'll have to download this.
It is 135 megabytes because of the videos, I think.
Ooh, okay, that may take a couple minutes here.
I already have it open here.
Oh, okay, Sid, would you take over then and do it?
Hold on. I have to check to make sure how I can do it.
Do I need to make you host?
Hold on.
Thank you, Sid.
Give me a moment here. Your PowerPoint is set to show in full screen mode. I definitely do not want to do that.
Okay.
Give me a moment to set the slideshow as kiosk mode, and I will.
Well, you obviously know much more about it than I do, Sid.
This. Give me just a moment here. Slideshow. Where is it here? Set up slideshow. Here we go. Individual window. Okay. All right. Slideshow. Resize the window. There we go. That matches your slide aspect ratio. Then share screen, share sound, optimize for video, clip, that. Is that what you want?
Yes, sir. Can I control this myself or do you folks do that?
No, you cannot.
Okay. Wonderful. Well, then I'll just
Say next slide. I'll be glad to handle that.
All right. Thank you, Sid. And again, good evening, everyone. And please accept my most profound apologies for the delay in being able to show you the presentation. It's really a pleasure and an honor to be able to speak at Balticon. And again, the subject of my presentation is what's new in optical physics and engineering. I'm going to focus on a few recent developments that have come out of the research in my laboratory at the University of Illinois. And let's go to the next slide, which should be a very short video. I just couldn't resist showing this to you. Let's go to the next slide. That's our attempt to make a lightsaber in our laboratory, and we just couldn't resist presenting that to you. Well, the first topic I'd like to share with you this evening is that of a completely new type of laser. All of us are familiar with lasers in that those of the past have generated a single beam. We're all familiar with the idea of having a laser that has two mirrors and there's something between the mirrors that generates the light, and then there is a beam that comes out one end. And this beam sort of looks like a pencil. Well, I want to introduce you to a new type of laser that produces not one laser beam, but literally thousands simultaneously. And if I could direct your attention to the diagram at the top of that slide, thank you, Sid. At the top, there's a simple diagram showing that we're going to change the laser by introducing an array, actually a two-dimensional array of microspheres. that rest on the lower mirror. And so we have a gain medium. That's a term that that we use a lot, but just to express it in more straightforward term to all of you, it's the medium that generates the photons. And then from the top, we're going to bring in green light. This is a laser that will help drive our system and produce laser light. So the beautiful thing about this system is that it produces many beams, one for every microsphere that you see in the diagram. The reason I wanted you all to see this is most of the slide is a set of false color images of a laser that's generating infrared light. And we find out that instead of producing a traditional laser mode or a laser beam that is more or less uniform across the beam, we can actually produce very unusual patterns. And some of them are shown here. Notice that there is a laser beam produced for every sphere. And what you're looking at is where we actually have a microscope that is looking down into the laser from the top. So you'll notice the dark circles, each one of those represents a microsphere. And the intensity of pattern that you see is a different type of laser mode. Okay, well, these are all very beautiful. And let's go to the next slide. Here's another photograph. Now this is in these photographs were taken in real color, and you can see that some very strange modes can be generated with this this new type of laser. I'll let you think about what they might mean, but I'm going to, for the sake of time, not comment on them further. Let's go to the next slide. Now, what I'm most excited about sharing with you this evening is that we have discovered an entirely different type of mode. Mode, again, refers to the transverse. If the beam is coming out towards you, then I'm talking about the mode intensity pattern that we see if we slice the beam in this direction. And quite to our surprise, when doing these experiments at the University of Illinois, we found that a new type of laser mode was emerging from the laser medium, but in the regions between those spheres that I showed you on a previous slide. So if we look at this larger photograph, again, we're looking through an optical microscope into the laser itself. Notice that at the so-called interstices, that is the regions between microspheres, and the boundary of the microsphere is shown by the dashed white curves. So if we look at the upper right part of this photograph, notice that there's a star type of image that is being produced. And it turns out that these are what are known as fractal modes. All of us are familiar with fractals in nature. For example, snowflakes are well-known fractals. There's even a type of broccoli, believe it or not, that produces fractal patterns. Now at lower left is another image at lower magnification showing the appearance of these modes by the red light. Notice at the intersection of three of the spheres, the microspheres, notice that there is a mode that's being produced that looks a lot like a crab. And then further to the left, you see that there is a mode that is forming. Now, fractals are really interesting. Let's go to the next slide, please. Fractals are really interesting because they are made up of a particular shape that is reproduced over and over at different spatial scales. That's why snowflakes take on the form that they have. So at upper left, I have a diagram that shows how these modes are formed. And in particular, if we have an intersection of three microspheres, we can expect that we're going to generate fractal modes that have the triangle as their basic shape. And so if you look over to the right-hand column of images, those are the highest resolution images we've been able to obtain to date. You'll notice that they represent different forms of a triangle. One of them in the middle looks like two triangles that are flipped by 180 degrees with respect to each other. And perhaps the most easily distinguished mode pattern is shown at lower right. We photographed this in one set of experiments. Notice that there's a stack of triangles. And in mathematics, this is what is known as a Sierpinski triangle. At lower left, you see that if we pull the spheres back from each other just a little bit, in other words, they're not in contact with one another, we can actually observe these modes beginning to interact with each other. And notice the sort of the fingers coming out from the mode at lower right. Okay, well, these are interesting. And by the way, the insets shown on the two panels at left are calculations of what the modes should look like. And indeed, they do. So let's go to the next slide, please. Okay, I wanted to show you some calculations of other types of fractal modes. And again, these are produced by a laser. They've never been observed before. And we were, I must confess, really overwhelmed by what we saw. These modes that you're looking at now are calculated modes, and we've begun to see some of them. Notice that all of them have a snowflake type of a look to them, and they're absolutely fascinating. Again, they've never been observed before. Okay, let's go to the next slide. Okay, now that we've talked about laser fractal modes that have been observed recently, let me describe a little bit more about what can be done with this new type of laser. Well, remember that as shown at upper left, there are two mirrors. The layer that's shown in red and labeled CQD is a type of laser medium known as a quantum dot. And we're probably all aware of the fact that some recent brands of televisions have begun to use quantum dots. Well, what I'd like to share with you is the fact that it turns out that we don't actually need a laser to, excuse me, a regular mirror to generate a laser. So we did some experiments in which a type of algae cell known as Chlamydomonas reinhardti, which we affectionately call clammy, can actually serve as the microspheres that you saw in the previous laser design. In other words, those green sort of algae cells that you see at upper left, and they actually do have antennae coming out. So that's why we drew them that way. They can actually serve as a lens, a small lens. It turns out that these cells are about 10 microns in diameter, but they're fairly flat. So they look very much like a lens. So in fact, it works. It turns out that if we introduce these living cells into the interior of the laser resonator, we obtain lasing just where the cells are located. So the four panels shown on the right are actually false color images where the blue circles or ellipses actually represent the perimeter of these clammy cells. And the red pattern in the center is actually a laser, a sign of laser emission. So at upper left of these four panels, you see sort of a red line, and upper right, there are three spots. So every time that that we that we fire this laser, we obtain a slightly different mode pattern. And we believe that that's because this is a living cell. And if you look at the images, you'll see that the insides are changing a little bit. And that's why the mode pattern is changing. At lower left, you can see red emission from inside several cells. And again, that's due to the fact that clammy is basically acting as a lens. Next slide, please. Okay, so I wanted to convince you that we can actually obtain thousands of laser beams from this particular laser. I won't spend long on this slide except to show you that we're now once again looking into the laser cavity, and you're looking at a portion of the micro laser beams that are being produced by this laser system. In this case, the laser light was being generated inside of a very thin crystal of sapphire, excuse me, that is doped with titanium. So the reason that the laser beams have this color is they're actually being emitted in the infrared. So let's go to the next slide. And I might say that while the slide is changing, that we've produced as many as 4,000 laser beams from these resonators. And they're only about a centimeter in diameter. So there's 4,000 micro lasers packed into about 1 centimeter diameter. Here are some of the other laser modes that we can produce, and some of them are quite interesting. In the third column from the left, most of the way down, you'll see there's a mode that looks like an S, and we've named it in honor of one of my graduate students at the university. Next slide, please. Here's a view, a larger view of more than 2,000 micro lasers, and I won't spend much time on it, but these are beautiful to behold. Next slide, please. Okay, well, you might say, well, that's really interesting, Gary, but what can we do with this? Well, it turns out that this laser that produces 2,000 to 4,000 micro laser beams has properties we've never seen before. One of the properties of most lasers is that because of a property known as coherence, and thank you for the question. And by the way, I forgot to mention this. I hope that we have some time at the end where we can entertain some questions. But these two slides are images taken of two different versions of the laser that I showed you a few moments ago. On the left, we only had 5 microlasers in operation. And these 5 microlasers are diffracting in the far field, and they're striking a surface. And you can see all of this, the gradations, the changes in intensity that are recorded by the detector. On the right, we have the same laser, but now there's approximately 1,000 micro lasers that are striking this surface. And notice that the intensity fluctuations have virtually vanished. So this laser is, in fact, a speckle-free laser. And you might say, well, why is that interesting? Let's go to the next slide. I wanted to show you a couple of images, one of which, the one on the left, was recorded with a conventional green laser. And it may be, in fact, it's impossible to tell, but underneath this, this green intensity pattern is the same biological sample that's shown at right. And at right, you're looking at a sample of spirogyra, which I think most of us probably remember from high school biology is an algae that can be found in any pond in the Washington or Baltimore area, the Delmarva area during the summer. So it's that familiar green covering on ponds. But this is what spirogyra looks like at high resolution. Everything is the same in this experiment, except we're using the 2000 microlaser resonator that I was showing you a little bit ago. And you can notice a couple of things: the double helix structure of the spirogyra. So the bottom line, my friends, is that images of extraordinary resolution can now be obtained. And if you're still not convinced, let's go on to the next slide. The video works. Okay, so we're looking at video that was recorded by using one of the lasers I've been discussing that has over 2,000 microlasers. And we are operating the laser pulse. That is, it's running at about 10 pulses per second. And all we did was we recorded an image with every pulse of the laser, and then we just stitched them together. So you're watching the cells. Some are not moving because they're attached to the walls of the optical cell, in which the clammy, these are clammy cells again. And so you see that one is spinning around, and that's because they do have a photoreceptor, a very simple eye, but you can actually see the internal parts of clammy. And if you look carefully, you can see the eye at the top. And some are out of focus because they're out of the focal plane. But I just wanted to let you know that images of very high resolution can be obtained. Let's go to the next slide, please. Okay, well, I wanted to let you know that that one of the beauties of this new laser is that if we do operate it pulse, we can obtain images that, to be honest, have not been accessible previously. We're looking at two images of the common fruit fly, also known to entomologists as Drosophila. And at left, the Drosophila is at rest, and in the right, it is in flight. And this image was captured with a single laser pulse that's 8 nanoseconds in duration, and that is so short that we can capture the image of the insect in flight without motion blur. These insects typically beat their wings at frequencies up to 200 hertz, 200 times per second, and that requires that the image be captured in less than about 100 nanoseconds. And you can see how the feet are extended behind the insect. So we don't believe that this type of an image has ever been observed before. Next slide, please. Okay, well, if I hopefully have convinced you that we can obtain very high resolutions of microscopic objects, or such as cells and flies and so forth. But now you're looking at a video that was taken with that same laser operating with more than 4,000 micro beams. And it is viewing a turbomolecular pump, the outermost rotor of the pump, while it's rotating at 56,000 RPM. We're viewing it from a distance of 2.5 meters. And the resolution is about 1/10 of a millimeter. Now, the reason that the fan is still moving, even though we are capturing these images with very short pulses is that the phase of the laser is not the same as that for the pump. So that's why the pump vane is moving. But I wanted to show you this to hopefully convince you that we can capture images that are also at a distance. Next slide, please. Okay, so I'm going to have to skip because we're running out of time. This is an image of a target obtained in the presence of a very heavy fog between the laser and the target. Let's go to the next slide. Well, there was a comment made by Homer Adkins many years ago about that said that basic research is like shooting an arrow into the air and where it lands, painting a target. I love this statement. And let me illustrate how it's worked out in our lab in a couple of cases. Next slide, please. So Sid, thank you for your note. So I wanted to show you this image. Friends, you are looking through a lens. This is a magnified view of the surface of a type of ultraviolet emitting lamp that's been developed in the past few years. And on top of that surface, we've sprinkled several diamonds. And this lamp, you can tell where the surface is because that network of hexagons that you're looking at is actually an electrode. And beneath it are some circles that of differing diameters that are emitting light. I won't bore you with the wavelength of the light. Suffice it to say it's deep into the ultraviolet. And the lamp is flat, very different from the lamps that all of us have grown up with, whether it's a bulb or a fluorescent lamp that's a cylinder or even LEDs. So these lamps are new, and I won't spend a great deal of time talking about how we developed them. The reason I wanted you to see this is that because the wavelength of the light is so short, that you're able to see things in materials that were not observable previously. So these diamonds are a combination of real diamonds, those that were dug out of the ground, and those that were synthesized. It's now possible to make artificial gems. So the bottom line is that the diamonds that appear to have the garish colors, the yellow and the deep burgundy, are in fact synthetic diamonds. Real diamonds are the light blue ones. So these lamps are actually being used now in commercial products that are being purchased by jewelers, gemologists, to identify or separate synthetic diamonds from real ones. The next slide is a picture of one of the lamps that is producing light at a shorter wavelength still. And the next slide shows what we can do with some of these lamps. The lamp that I just showed you on that last slide is emitting at 172 nanometers. That's in a region of the spectrum known as the vacuum ultraviolet. And it's named that because in the 1800s, it was found that this light has such a short wavelength that it's absorbed quickly by air. So they had to evacuate their experimental systems to be able to work with it. Well, what we found is that we can make some very spectacular structures in polymers, for example. And the next slide gives you an example of some of the things that we can do. So you're looking at an image that was recorded by a laser, what is known as a laser confocal microscope. And this image was produced by shining that 172 nanometer radiation light that I was showing you on the last slide through a mask. and onto a piece of ordinary acrylic polymer known as PMMA. And this is, of course, the image of Space Invaders. We couldn't resist showing this to you. But I just want you to know that the depth of that pattern, where the blue surface is, the distance from that blue surface to the top surface is only 240 nanometers. So we're making structures at the nano level. Let me show you a couple of others. Let's go to the next slide. This is what is known as an optical grading structure. Again, it's made in the surface of a polymer, and the height from the bottom, the blue regions, to the top in red is only on the order of 600 nanometers. The spacing between these square peaks has been chosen specifically so that it will diffract light. So if you look at the photo at lower right, on the left, notice that that black cylinder is a red laser. And although you can't see the beam is going through the plastic piece sitting on top of the metal, the circular metal piece, and it's diffracting light onto a screen. Notice the arrays of laser light shown at right. Okay, that's the signature of an optical grading. And so what's really exciting about this is that we can make very sophisticated optics out of inexpensive plastic. This is commercial grade plastic. So we make very sophisticated optics. Let's go to the next slide. And so all of this, my friends, has led to what we call the emerging field of nano art. We can make extraordinary structures. There's just a couple of examples shown on this slide, just to give you an idea of what can be done. And I must confess that I'm not an artist. I'm sure many listening to this presentation are much more experienced artists than me. But I'll just say this, that each of the layers, as you see at the bottom of this slide, is 250 nanometers thick. In other words, the red layer, the orange layer, green, and so on. And so these are very small. I mean, it's about approximately 5/1000ths of the diameter of the hairs on your head. So we can do some fun things. And we're showing these things because we would love to plant seeds in the brains of very smart people, and in the hope that you'll immediately see opportunities for applying this technology. Next slide, please.
Did I miss the next slide request?
Yes, if you could please go to the next slide.
Sorry about that.
No, nothing to be sorry about, my friend. So I wanted to introduce you to something we call water optics. And that may sound strange, but one thing that we found is that this vacuum ultraviolet light that I've been describing to you, that can now be produced at very high power levels, does strange things to surfaces of materials. And in fact, as you see it left, what we've done is expose a polymer to this 172 nanometer light through a mask. So, and then after we took the plastic out of the chamber, we dropped water onto it. And what that, it turns out, is happening is that the 172 nanometer light is making the surface hydrophilic. And by that I mean that water doesn't ball up on a surface like we see on our windshields in a storm, but it literally smooths out. So, for example, in the squares at left, if you look carefully, you'll see interference fringes, optical interference fringes, and that tells us that the water is just a smooth, continuous curve over the surface. And it's thickest at the center, which is what you would expect. At right, you're seeing a series of vertical lines that have been made in the surface, again, in a plastic, a polymer. And you can see that this is clean water, but you can see that the color changes as we make the lines thinner. And so what's happening in each of these lines, the water is just um, um, forming a curved surface because of surface tension. And you might say, "Oh, that's nice, but what can I do with that?" Let's go to the next slide. We can have some fun with this. So here are some more lines. And the lower portion, there's a number of lines that are equally spaced, same width. Next slide, please. Okay, so what we can do is make a grading, just like you've seen before. And notice in the right-hand photo that with a red laser, we're hitting this series of lines that you saw at the bottom of the last slide. And it forms a grading, but it's a diffraction grading, but it's made of water. Next slide. Let's do something a little bit more interesting. Oh, okay. This is a photo of the units in which we do this. So we're trying to make this technology so it is as useful as 3D printing. 3D printing 20 years ago was very expensive. Machines would cost several $100,000, and today 3D printers are, as you know, being used for a wide variety of things. So these units are only, they're very small and the size of a coffee cup. Okay, enough about that. Let's go to the next slide. Okay, I wanted to show you this. This is a video where we have made what is known as a Fresnel lens by irradiating plastic through a mask in the way that I showed you a little while ago. But the pattern that we impressed into the surface of the plastic is that for what is known as a Fresnel lens. What is a Fresnel lens? If you've ever been up into one of the older lighthouses along the Atlantic coast and the Pacific coast, you'll see huge glass lenses that where the surface comes out like this, and then it comes in, and then it comes out at an angle. That's a Fresnel type structure. So what are we doing here? What we're doing here is we have this Fresnel structure, and there's we're going to have to quit here in a few minutes, but there's nothing on it initially, um, but a laser beam is being directed onto the back surface. And then periodically, one of my graduate students is just breathing onto the other surface. And you can tell that when he breathes, you get this right here. You see this beautiful spot at the center. It's now the lens is operational. Why? Because he's breathed onto it, and the vapor is only adhering to the surface in the pattern of the Fresnel lens. When the when the vapor from his breath dissipates, you get this this hazy uniform red from the laser just going through the plastic. Okay, so I wanted to convince you that you can make some really really interesting optics, and we're thinking about applications of this for sailors, for example, where there's a lot of water vapor in the air. Next slide, please. Okay, here's some other images obtained with that same Fresnel lens. I won't belabor them because I'm running out of time. Next slide, please. Okay, I'm just going to end with this. I thought you might be interested in this. This does not involve a laser or optical systems per se, but it comes pretty close. We've actually succeeded in making very sophisticated crystals out of plasma. In this figure that you're seeing at left, each of the purple rods represents a plasma. Plasma, as you know, the sun is made from plasma. And we see it in a variety of different ways. I'm not referring to human blood plasma, but rather to that energizes stars. We've actually succeeded in making crystals such as the one you're seeing here. And the next slide shows a picture of a less sophisticated one. This is a structure at left known as a woodpile structure. And the crystal is operating at right. You see these columns. We tilted the crystal intentionally so that you could actually look into the crystal. And you're probably wondering, why is this sort of a reddish blue? And it's because each of the columns is made from a plasma and helium gas. Okay, when it's energized electrically, it emits this sort of reddish blue color. One of the crystals is actually shown at lower center, and you can see that it's the size of a US quarter. The active area of the crystal is 26 millimeters square. Next slide, please. So if you're wondering, well, what do I do with these crystals? It turns out that they act like regular crystals, that they diffract electromagnetic radiation. In this case, we're at frequencies of about 150 gigahertz. And if that is not meaningful to you, that's your cell phones operate at about 2.5 gigahertz. So this is what, a factor of, wow, 60 larger. And so depending on how the crystal is oriented, the transmission of this crystal that's made from plasma, for heaven's sakes, it's a transient medium, but by turning the plasma on, we make it, in a sense, come alive from an electromagnetic standpoint. Next slide, please. Okay, so time has passed me by, and again, I do apologize for
Dr.
the.
Eden,
Yes.
why don't we invite you and everybody to go to the con suite? There's a breakout room in con suite called Homeland Science, and you can continue the discussion there without your slides and see everybody and talk to them and answer the questions that you have that they might have brought up. So there, if you go to schedule.balticon.org and you look in the info section, you'll find the link for the con suite for today.